would be are there values for Z0, the number of zombies that we start with at the very beginning, so that Z sub t stays at Z0 forever. So it never changes, it never moves off of that value.
What about 0?
Alright, so what about 0? If no one has the flu, can anyone ever get the flu?
As long as you're including every, well, no, because
We're not, our model doesn't take into account genetic mutation or anything like that. It's just, no one has the flu, no one can pass it on. If no one can pass it on, nobody's ever going to get it. So in our simplified model that doesn't take into account mutations,
So how did the first person get
we
it?
get 0. Oh, that's a, well, then you have to include genetic mutation into your model,
Oh, okay.
which would then make it a much more complicated but interesting model. So this here is an equilibrium, because if you start there, you never get off of it, you never change away from it. The other question that we're going to be interested with equilibria is their stability. So, if I'm looking back at my erasers, even though every time I flip this eraser around the long axis, or Keith flips it around the long axis, we started in a little different position, we give it a little different push, we give the push in a little different way, so even though I change the way I actually start it going each time, and it's a little different each time, it still settles down into just nice rotation around the long axis. So we call that a stable equilibrium. Even though I start it slightly off each time, I don't start it in exactly the same position, it settles back to that nice rotation around the long axis and stays there. So that would be a stable equilibrium. A stable equilibrium is one where if you start a little ways off, you naturally fall back into that equilibrium. If you've ever ridden a bike, which I presume we all have, or at least you've seen movies, if you've ever tried to balance on your bicycle when it was not moving, can you do it?
You can, but it's really, really hard.
Without moving at all?
No.
No. So even those people who actually sort of, you'll notice that they're moving quite a bit to keep their bicycle up, even though the bike isn't really traveling down the road. That is an unstable equilibrium. If you could line everything up perfectly and get your mass perfectly centered and everything on it, sure enough you would stay up. But the moment you get just a little bit off of perfectly aligned, gravity pulls you more one way than the other and you fall over. On the other hand, when you're traveling down the road, do you have any problems staying up? So once you start into motion, then staying vertical on your bike actually becomes a stable equilibrium. Even though a gust of wind will come along and push you off to one side, or somebody's coming down the road so you have to swerve, and so you get a little off of your equilibrium position of being vertical, you naturally come back to that equilibrium position. You don't fall down, you come back to being straight up on your bike. You have to get knocked a long ways off of your equilibrium position before you'll actually fall down while you're traveling down the road. So that's the difference between a stable and an unstable equilibrium. Would this be a stable or an unstable equilibrium? If we start a little ways off of 0, do we naturally fall back to 0, or do we move away from 0?
move away.
If I start with, say, one person who has the flu, then what happens? We went through that.
All heck breaks loose.
Yeah. Now one person starts passing it around, they pass it to other people. Pretty soon you've got more and more and more people with the flu, and so you move away from your equilibrium position. So this is an unstable equilibrium value. If nobody's sick, nobody's going to get sick. But the moment one person gets sick, it's going to start to spread.
So the Earth and its wobble, is that considered an equilibrium?
Mm-hmm. It's
I mean, it tilts back and forth, but it stays in that range.
yeah, it doesn't shoot away from its equilibrium value. Now, it's a different kind of equilibrium. They're called cycles, where instead of staying in one position, what it is that you cycle through a set of values, but you always come back to that same original value, and you stay on that cycle. So you don't move away. To be an unstable equilibrium, once you get off of your equilibrium position, you actually shoot away from your equilibrium position. So if the Earth's wobble were unstable, the Earth would tumble, which would be fascinating to say the least, since that would mean that we went from being in the northern hemisphere to the southern hemisphere on some sort of regular basis.
Sure, the environmentalists would
There would
love
be times at which we would basically be the equatorial position of the Earth, and then we would move off of it, become the Arctic and the Antarctic.
Environmental equality, right?
So, yeah, how about complete chaos? Which actually a tumble is a chaotic behavior. So, other questions about equilibrium?
I was just gonna say, would Z not equals M be another equilibrium?
So, if we start at the maximum population, everybody's sick, what happens?
People get better, people die.
Yeah, but everyone's been infected, and so in terms of people getting infected, is anything going to change? No, we got everybody infected, so we're done. We're never going to change from that. If I start a little ways off from this, not quite everyone's infected, according to our model, not talking about completely realistic model here, but according to our model, what would happen? Eventually they would get infected. It'd take a little while to do it, but we would get everyone infected. So if you start off from this equilibrium, what happens? You will naturally return to it. And so this one is a stable equilibrium. If you start someplace off from it, you'll come back to it. Questions about the definitions?
Is a stable equilibrium kind of the same thing as steady state equilibrium?
Any equilibrium, in one sense, is a steady state. If you don't have anybody sick, that's a steady state. You're just going to stay there. So the parlance changes depending on where you are, what application you're doing, whether you're in biology or physics or engineering or where you might be. If you're in engineering, then you'd be a stable equilibrium would be a steady state equilibrium. But if you're over in biology, they don't use the word steady state that much anyway. But if you did, I suspect that they would just think you were talking about an equilibrium, not necessarily whether it was stable or not. Good question. Others? All right. Let's come back up to what we have up here, just to make things a little easier. Let's let this z sub t plus 1 be our y. We'll call it y now. Why, I don't know, but... And we'll let x be z sub t. That's just to get it into some more familiar notation for the analysis that we're about to do. If we take our difference equation over here, rewrite it in terms of y's and x's, we have y minus x is equal to kx times n minus x. So I can add the x over. If we go and multiply it all out, we get why did I do that? I don't know. There we go. So we have that. And if I multiply this out, which is all I really wanted, I have kmx minus kx squared. I could rewrite it as a nice little polynomial equation in y. So we would have, might as well do it. So if I was writing it as an equal
Plus
to
1x?
yeah, that would be helpful, wouldn't it?
Yeah.
There we go. Thank you. As I say, I majored in math, not arithmetic. So we have that. That's the way we're used to seeing just regular equations being written down. And so we can take regular y equals x squared kinds of equations, and we can do the kind of analysis. We can treat them as if they were discrete dynamical systems. And we can do this kind of analysis over here. Or we can take our discrete dynamical system and we can use this formulation of it in terms of it just being a nice little polynomial as our, and try and see if we can get some insights into the difference equation from this perspective. Now if we come back here, I can factor, we can factor out an x. If we do the usual thing that we always did in algebra classes to this kind of stuff. And then what was the thing you always did with these kinds of functions back in Algebra 1, Algebra 2, college algebra? And you always wanted to find where it was equal to 0. And so we would find the zeros of this thing, which would be where?
0.
X equals k plus 1 over k.
And x equals m plus 1 over k. Why were we interested in zeros? What use was that ever to you?
Those are the times when 0 people are infected.
Well, those are the times when, if we look back at it, why is your...
Oh, and I guess there's no change. I guess.
Yeah, when the change of people.
Yeah, when you reach equilibrium, actually, right?
Go ahead, Lisa.
Wouldn't you want equilibrium to be if we were back on our z of t plus 1 minus z of t, so it's your change equal to 0?
So what would a 0 down here mean? The y is just what? Number of zombies at the next time. And so when y is equal to 0, we would be looking at times when we have
No zombies in the next round.
no zombies
No
in the
new
next
zombies.
round. Yeah. No zombies in the next round, regardless of how many zombies we might have in this round. So it certainly makes sense in terms of our model that if you have no zombies, you're not going to get any. What's this thing?
Well, it's the entire population plus some small number.
M plus 1 over t.
So it's
Yeah,
the
this
built-in
is...
action.
Oh, excellent. So you're rewriting this. So if we split up this fraction, it's m plus 1 over k. Does that mean anything?
I mean, those are like the two equilibriums that we talked about.